Good morning. Welcome to the lecture on pulse transfer function. Normally, for continuous time systems, the transfer function is defined as the any transfer function. Let us say it is g of s. It is the Laplace transform of the output variable c of t by the Laplace transform of the input variable r of t. For example, when c of t is the output variable and r of t is the input variable to the given system, a system, if you can consider it as g of s, you can say if you are applying r of t as input and c of t as output, or in the Laplace domain r of s and c of s, you can say that g of s is equal to c of s by r of s. And here we are assuming all initial conditions to be 0. Initial conditions are assumed to be 0. That is the definition of transfer function n by dealing with continuous time systems. Similarly, for discrete time systems, we call it as, we have a similar transfer function. That transfer function for discrete time systems is called as pulse transfer function. And what is this pulse transfer function? Is given by g of z, which is nothing but, you can also call it as c of z by r of z, where c of z is the z transform of c of t. Z transform of c of t, you can call it as z transform of c of t, and which is nothing but z transform of r of kt, which are c of kt and r of kt are the sample data obtained from the continuous time signal c of t and r of t. Therefore, this is the pulse transfer function. Now we are going to define how we are going to obtain pulse transfer function for any discrete time systems. Before going into this discussion of pulse transfer function, we are going to first analyze what is a convolution summation, because you are dealing with any two, you are dealing with two continuous time functions. Therefore, you have to deal with convolution summation. This is the term used in analogous with convolution integral, which is used for continuous time systems. The convolution integral is used for continuous time systems, and for discrete time systems, this is used for discrete time systems. Convolution summation is used for discrete time systems. So we will try to see what is convolution integral. Convolution integral is nothing but, for example, any output y of t is nothing but the convolution integral over g of t minus tau x of tau d tau, or you can also write it as integral 0 to t x of t minus tau g of tau d tau, where g of t is the weighting function and g of t is assumed to be 0 for all time t less than 0. That is, t is existing only from 0 to t, and it is not existing below the values of time t equal to 0. Right? Or you can also call it as, g of t can also be called as the impulse response. The impulse response, g of t is the impulse response of any function x of t. Therefore, of an impulse function x of t. So you have y of t is integral 0 to t g of t minus tau x of tau d tau. when this is happening, a similar relationship here, that is in this convolution integral, if you are converting it into, in this convolution integral, if you are converting it into the applying Laplace transforms to this, any convolution integral y of s is equal to g of s into x of s. It is a direct multiplication of g of s and x of s for any system g of s and the plant g of s, the output y of s for any input x of s. Therefore, y of s is equal to g of s into x of s, you can call it as, or y of t, you can call it as g of t star convoluted over x of t. So this is convolution integral in the continuous time system. Now a similar relationship we would like to introduce in the convolution summation. So we will see for discrete time systems what is convolution summation. Convolution summation is used for discrete time systems. Now let us say we are having a system, a signal x of t is applied and a sampler del t, you can say, and a function g of s is given here, and I am getting an output y of t, and so this function will be x star of t. Now this can be called as an input sampler with time period capital T. This is the input sampler which we are having the time period capital T, and x of t is our continuous time signal. Therefore x star of t is our train of impulsed signals, and which, when this is applied as input to the system g of s, then you will have an output y of t. So what is the z transform of y of t? And y of t obtained is also an impulsed signal. Therefore you can say that sigma k is from 0 to infinity y of kt z power minus k, y of kt z power minus k, where now if I also introduce an output sampler here with the same del t, then I get here y star of t. Then I can call it as output sampler, which is synchronized with input sampler with the same time period t. Both input sampler and output sampler both are in phase with each other, synchronized in phase with each other. Therefore we will not lose any information while sampling the data, continuous time signal, or reconstructing back the continuous time signal. Therefore when you are having this, the same y star of t you can also call z transform of y star of t is equal to sigma k 0 to infinity y of kt z power minus k. So for both these signals, even if you are using an output sampler here or not, the same signal, the same equation can be used to determine the output of the output that is coming from the plant. So with this in mind, we will try to understand what is the by using the convolution integral y of t, I want the output y of t. So if I am using the integral 0 to t, the convolution integral term g of t minus tau x of tau d tau, g of t minus tau x of tau d tau, and x star of t, when I am using this x star of t, what is x star of t for us? It is already discussed in our impulse sample signal, impulse sampling. You can say that it is k is from 0 to infinity x of t minus kt x of kt into del of t minus kt. Because the sampler is a train of unit impulses, and which is where you will be getting x of t. So x of kt into del of t minus kt, you are having x star of t. So when you are going for this, we are having y of t is the convoluted multiplication of g of s and x star of t. Therefore, I will put x star of t here, because y of t is the product of g of s and x star of t. So when you are convoluting these two signals, you can say that when you are replacing g of t minus tau, x star of tau you can replace it with sigma k is equal to 0 to infinity. Here I am using tau, therefore instead of t I will use tau here. So when I use tau here and here, I can replace this with x of k tau del of tau minus kt d tau. Right. So we are having this relationship for y of t. So continuing with this, y of t is equal to, you have this, without any loss of generality I can go with k is from 0 to infinity, integral over 0 to t g of t minus tau x of k tau del of tau minus kt d tau. Right. When you are having this relationship, we are going to replace this with sigma k is 0 to infinity, and you can see here g of t minus tau del of tau minus kt and d tau. You can have this x of k tau, and the product of these three, the integral of these three, you can make it as g of kt minus g of tau minus kt. So you are having this relationship from sigma k is 0 to infinity x of k tau g of tau minus kt, and instead of tau you can easily replace it with k is equal to 0 to infinity x of kt g of t minus kt. Now this is the relation which we have obtained for convolution summation. Therefore y of t can be given as sigma k is from 0 to infinity x of kt g of t minus kt. Now with this in mind, we can go for the pulse transfer function. Now let us have a small relationship between convolution integral and convolution summation. Convolution summation, you are having the relationship y of t is equal to sigma k is 0 to infinity g of t minus kt x of kt, or you can also write it as sigma k is from 0 to infinity x of t minus kt g of kt, and for convolution integral you can write that is integral 0 to t g of t minus tau x of tau d tau, or integral 0 to t x of t minus tau g of tau d tau. Now you are having these relationships. When you are having this, you can just see that what is convolution integral. You can say that you are having y of s is equal to g of s into x of s. This is convolution integral for us. Any two time domain signals, when you are trying to multiply or convolute you can directly product those two signals in the frequency domain or the using Laplace transformations. Similarly here, y of t is equal to, you are having two different x of t minus kt and g of kt, or g of t minus kt and x of kt. So you are having these two relationships, convolution summation. In convolution summation used for discrete time systems and convolution integral used for continuous time systems. Now with this, we will try to understand what is pulse transfer function. Pulse transfer function that we are going to discuss here. Now y of t is the output. Y of t is the output that we are going to obtain for a signal which we are having it as g of s and y of t. Here we have x of t or x star of t and del t, which is the sampler. For this signal, y of t is the output and g of s and x star of t, these two are convoluted, or convolution summation is happening in this form. So I need to obtain the z transform of y of t. The proof for us here, what we require is y of z is equal to g of z into x of z. This is what we are trying to prove in our current discussion, where z of y of t is nothing but sigma n is equal to 0 to infinity. For example, let me say, because I have already used k is equal to 0 to infinity here, I will have y of kt z power minus n. So this can be called as z transform of y of t. You call it as y of z, which is nothing but sigma n is equal to 0 to infinity. And what is y of kt here? We are having sigma k is equal to, k is 0 to infinity, g of nt minus kt. Instead of t, I am replacing it with nt into x of kt z power minus n. So this entire term you can call it as y of t, or this is y of t which you have replaced there in this equation. So this is the term that is replaced, this term is replaced here instead of y of kt, right? So with this in mind, you can just see that here I have n minus k. Let me say n minus k is equal to m. Then when n is equal to 0, m is equal to minus k, and n is equal to infinity, m is equal to infinity. And we know that g of t is equal to 0 for all t less than 0. It means that g of nt minus kt is equal to 0 for all n less than k. When this is happening, therefore m is equal to minus k, you can replace this with 0 without any hassles. Therefore y of z, from here you can take that sigma, replacing n with m is from 0 to infinity, sigma k is from 0 to infinity, g of n minus k, which is equal to m, you have mt into x of kt z power minus n. Now what is n? N is equal to m plus k. From here you can say that n is equal to m plus k. So when I replace n with m plus k, I have this equation written as sigma m is equal to 0 to infinity, sigma k is equal to 0 to infinity, g of mt x of kt z power minus m z power minus k. Now if I separate these m and k terms separated, when m and k terms are separated, m is equal to 0 to infinity, g of mt this is m is 0 to infinity, g of mt and z power m minus m is taken separately, and again sigma k is from 0 to infinity x of kt z power minus k. Now you can see that y of z is equal to, now without any loss of generality, by definition of z transforms, we can say that this is equal to g of z, because this is m and m here and m here. Therefore you can say that this is z of z transform of g of t, and this is x of z. Therefore this equation y of z becomes g of z into x of z. Right. So this is what we have proved here in this pulse transfer function, and therefore g of z, when you divide throughout by x of z, you get g of z is equal to y of z by x of z. Now what is y of z for us? This is the z transform of y of t, which is the output of the system, and x of z is the z transform of x of t, which is the input of the system, the continuous time system. Right. So g of z is equal to y of z by x of z is what we have found out from this pulse transfer function using convolution summation. Right. So convolution integral is the definition that we are using for continuous time systems, and convolution summation is used to convolute any two signals in the z transforms, that is in the discrete time control systems. Right. So we are having the pulse transfer function as g of z is equal to y of z by x of z. Now let us see what is starred Laplace transforms under this pulse transfer function. Going ahead with the pulse transfer function, you can say what is starred Laplace transforms. Starred Laplace transforms. Already we know a particular equation which we have derived, which is x star of s when s is equal to 1 by t ln z. This is equal to x of z, which is equal to sigma k is equal to 0 to infinity x of kt z power minus k. This we have already discussed in our previous classes, where x star of s, which is called as the starred Laplace transform, which when s is equal to 1 by t ln z, that is equal to x of z, or you can also call it as z is equal to e power st. These both are equivalent terms, right? So when you are replacing z is equal to e power st, you are having a s domain function, or when you are replacing s with 1 by t ln z, you are getting a z domain function. Right. So using this into our consideration, you can say that, for example, let us say we are having a continuous time system x of t, del of t, x star of t, and this x star of t is acting as input to g of s, and we are having y of t here. So when you are applying Laplace transforms to this, we are having x of s here, x star of s here, g of s and y of s. Now according to this equation, to this diagram, we can say that y of s is equal to g of s into x star of s. Y of s is equal to g of s into x star of s. That is a simple Laplace transformations. When you are applying for a continuous time system, you are getting g of s into x star of s. Now when you are applying star Laplace transforms to this transfer function, now you can just observe that x star of s is a sampled data signal. G of s is only a continuous time signal. It means that you are having in this diagram, you are having both starred Laplace transforms as well as normal Laplace transformations. So when you are having two different Laplace transforms, that is, one is the normal Laplace transformation and the other is the starred Laplace transform, then when you are in a need to obtain the starred Laplace transform of y of s, that is when you are applying some other sampler here in phase with the input sampler, if you call this as the output sampler and this as the input sampler with the same time period t, then you are going to obtain y star of s here. So if you are requiring y star of s, then the output here for this transfer function is g of s into x star of s, the whole star. Now we are in a need to find out what is the meaning of the starred Laplace transform of y of s and what is the meaning of the starred Laplace transform of g of s into x star of s. So we will have to understand what is happening inside when you are using different samplers at different points in the block diagram. So with this in mind, just we will see that what is y star of s? This is g star of s into x star of s. Now we will have to prove this. We have to prove that y star of s is equal to g star of s into x star of s. Here x star is already a sample data signal and star indicates sampling, right? Already a sampled signal need not be sampled, so x star of s is as it is x star of s, and here this is a continuous time signal and it has to be sampled, therefore g star of s. That is why we are having y star of s is equal to g star of s into x star of s, which we will try to prove it in this class. Right. So let us say we will use this equation to prove this equation. We have y of s is equal to g of s into x star of s. Now this is nothing but convolution integral of two different functions. It is the convolution integral of two different functions. Therefore, if I want y of t, what should I do? I will have to apply inverse Laplace transforms of y of s. Inverse Laplace transform of y of s to obtain the continuous time signal. So what is this? The meaning of this here? Laplace inverse of g of s into x star of s. Inverse Laplace transform of g of s into x star of s. Right. So here inverse Laplace transform, I get continuous time signal. Therefore, I will have 0 to t g of t minus kt, or you can say here t minus tau x of tau d tau, or because you are having star transformations here, I will apply star here. So integral 0 to t g of t minus tau x star of tau d tau, and hence when you are applying this here, integral 0 to t g of t minus, or you can also call this as x star of t minus tau g of tau d tau. So when you are applying inverse Laplace transforms to this transfer function, then you are going to have to this combination of, or the product of g of s and x star of s, you are having these signals.